Okay, I think what we can do is we'll just get started and yeah. Perfect. So hello, everyone, and welcome to week 2 of Finovate at Discover Tech 2022. We hope you enjoyed our previous sessions and also had the chance to check out some of the other tracks from session or week 1 as well. This morning, we have a great workshop planned for you run by Marius Zoican, a finance professor at the University of Toronto and the Rotman School of Management. Within his accomplished career, he studied the impacts of new technologies on trading and stock exchanges, and also works to understand how to best leverage innovation to build the markets of tomorrow. He also frequently collaborates with leading Canadian market participants, such as the TMX Group, and he is featured in mainstream media, such as in The Economist, BNN Bloomberg, or Toronto Star. Please join us in welcoming Marius Zoican.
Thanks a lot, and thanks for inviting and having me here. This is a great event to be at. I was thinking quite a bit about what's the best topic to talk about. My personal research is more in stock markets, but I feel like a topic that could be relatable to everybody, and it's I can sort of get my hands dirty and show you how it really works. Is the issue of banking and big data, right? Everybody has seen somebody that wants to get a loan. Get a mortgage to buy a house, get a loan on their car, apply for a credit card, right? So the bank has to make decisions. Who's going to get a loan? Who's going to get the credit card? What kind of credit limit are you going to get? And beforehand, maybe you'll have just a one-on-one with your banker. He'll try to understand what kind of person you are, whether you're likely to repay your loan or not. These days, it's much more data-driven. The process is much more data-driven. So the bank has or collects huge amounts of data about you. What's your income? What's your net salary? What's your net worth? What's your credit score? Are you in debt? How much debt do you still have to pay on your car and so forth? And try to collapse this huge data into one number, right? It's a yes/no decision. Do I give this person a loan that they're asking for or not? So what am I going to do today? I'm going to show you a little bit of the underbelly of how modern banks leverage this big data to make this decision, right? And some newer platforms and your fintech platforms like for example, Lending Club, they do these decisions automatically, right? There's almost no human intervention there. They just collect the data, process it, and the data spits out a yes, this person is qualified to receive a loan, or no, it's not. And please feel free to interrupt me at any point, and we can have a conversation. A lot of the items on this set of slides might be technical. I'm going to try to provide like a very high level intuition, but just, if you're unsure about something or you want to know more about something, just feel free to raise your hand or put me here in the chat. You can all see what I'm doing. You can all play with it individually. So I'm going to put a link here in the chat. I'm not sure if you can see the link. I'm going to send it again. So every one of you has access to this notebook that I have on the screen, and can just play with it independently. It's not going to affect what I'm doing here. All right. So what we're going to use today, we're going to use Python. Python is a programming language that's very used in the financial industry. So I'm going to use this as a backdrop for everything that I'm going to show you. Right. So as again, the main idea is what I told you. You have a lot of data about somebody, right? Their income, their debt, their net worth, their credit score, etc. So every sort of data point you have, it's called in sort of like machine learning parlance is called a feature, right? It's a variable. It's something that you're using to guide your decision whether that person should receive a loan or not, right? And your decision is literally binary. It's 0 or 1. 0, no, I'm going to refuse the loan. 1, yes, I'm going to grant the loan, right? So your big problem is how to compress all these variables and the huge amount of data that's out there, how to compress it to a yes and no, right? And that's sort of the first challenge. It can become mathematically a bit involved, but it's not so complicated if you sort of focus your mind on what the end goal is, right? So let's say you have all these variables. X1 could be your salary. X2 could be your current outstanding debt. X3 could be your credit score. And you're just sort of adding them up all together, right? You multiply them by some coefficients, by some numbers. Those coefficients represent how important do you think income should be in the loan decision? How important do you think your credit score should be for the lending decision? So you're just bundling everything up together and you're getting a new variable called Y that sort of summarizes everything you know about that person, right? And then this variable Y will be essentially a number, but the number doesn't really tell you yes or no. You want something that's sort of in between 0 and 1, in between the bad outcome and the good outcome, or ideally at the margins. So what you're going to do with this variable, you're going to sort of put it in a function, in a nicely behaved function that always going to give you a number between 0 and 1. All right. So if somebody with very low income, a lot of debt, no house ownership will have a Y variable that's closer to 0. It's going to be here on this end. So the probability of giving them a loan is very, very low. People with very high income, low debt, they own a house, they have a great credit score, they're going to be somewhere here, closer to 1, right? And everybody else is going to be in between, right? And this number between 0 and 1 is the probability that they're going to repay, they're going to give the bank the money back, right? This is going to be their success probability. So now your challenge as the coder, as the banker, is to find out exactly what should the weights be. How much importance should you allocate to each of these variables? How much importance should you allocate to the income? How much importance should you allocate to the credit score? How much importance should you allocate to the fact that whether the person owns a house or not already? That's your job. And there's no other way to get around this but using past data, looking at your past loan decisions and seeing what are the features of the people that did well. What mattered most in the past, and then I'm going to assume, well, what mattered most in the past is going to matter most in the future, right? So this is a quite quantitative, mathy approach to the problem of giving somebody a loan, right? So let's sort of get our hands dirty, right? And that's what I sort of wanted to give you this, and look at actual real life data from a fintech platform called Lending Club. A Lending Club allows you to give loans, put your money on the platform as a retail investor, as a student, as somebody who just started out, and you are matched with a person that wants to borrow. They want to get a new car. They want to finance their next holiday or their next wedding. Okay, so here I'm going to start coding. I'm going to load some libraries, some collections of functions I'm going to need. I'm going to need NumPy to perform computation. I'm going to need pandas to sort of manage a database, and I'm going to need some plotting functions. Then I'm going to load the data. I have a data in an Excel file somewhere stored on my teaching GitHub repository. And I'm going to read it. I'm going to read the Excel. I'm going to show you the first 5 rows. So these are, each row here is an individual, right? And you can see I have 4 variables that I'm going to use in my data. Home ownership, do they own a home or not? 1 stands for yes, yes, they do own a home. 0 stands for no, no, they do not own a home. Their income, and there's income in thousands of dollars. So the first person has an income of 44K, second income 38K, 54K, and so on and so forth. This first column, which is quite mysteriously called DTI, it's the debt to income ratio. Like how much debt do you have compared to your yearly income? So the first person has 18%, right? Debt to income ratio, second one, 33%, debt to income ratio, and so on and so forth. The FICO score, that's the credit score, 690. Remember, FICO scores are like in the US, like in Canada, like the Equifax scores range from 0 to 800. So 690 is pretty good. 660, 695. And then the loan status. And that's what happened when they had to pay back their loan. 0 means they failed. 1 means they were successful, right? So all these 4 people failed. I can plot you some data and plot each variable. For example, the FICO score, you see most people have FICO scores around 675, 700, with a few of them having sort of values over 800, 825. These are like they're really good credit scores. I can plot you change the variable here, the income. And you can see the income is somewhere around 50K on here, with quite a few people making 200, 400K. So I'm not sure why necessarily they have to go to lending club to finance stuff. And if I look at the loan status, you see that most people actually manage to pay back their loans, right? This is 1, this is yes, I paid back my loan. This is 0, I did not pay back my loan. So in this data, the snippet of data that I show you, we have about 8,695 loans that were given by Lending Club. And out of these, almost 7.2K, so 196, they came through, right? The people paid their money back. And a small fraction, 1,499, defaulted on their loan, right? So my goal as the banker is to look at this data and figure out which features are important and figure out how to best distinguish between the people who are going to be successful in the future or people who are not going to pay me back in the future, right? I want to be able to distinguish. I want to give out loans to everybody who's actually going to be successful. And I want to not give any loan to the people who are going to fail, right? In an ideal world, that's what's going to happen. And I'm not going to make any of the 2 potential errors. One is a type 1 error. It's an error of not giving a loan to somebody who deserves it and who's going to repay me, because I'm losing the interest there. The second is giving a loan to somebody who's going not to pay me back, because in this case I'm losing the entire principal. I'm losing everything I gave him, right? So I want to sort of avoid as much as possible both errors. Okay. Are there any questions or thoughts by this point? I'm not sure how exactly you want to do this, or should I proceed? Okay, before all good, I'm gonna move forward. So the first thing I want to do here is I'm going to process the data, right? I will first have to separate these first 4 variables. First 4 variables are the predictors, are the variables I knew going into the loan, from the 5th variable, which is the outcome of it, right? So these, if you look at the beginning of my presentation, the first four variables are the x's, and the fifth variable is the 0, 1 that I'm interested in. Okay. So how am I going to do it? I'm going to just drop the loan status to keep everything else, and I'm going to put them in a database that's called X-Train, right? This is the data set that I'm going to train my model, my machine learning model on. I'm going to teach it how to distinguish between good and bad loans. All right, so all the pieces of code are doing is sort of separating the outcome from the inputs to the model, right? And then the y variable is going to have the output. That's just the loan status. Okay. So once I do that, I need to employ the actual machine learning techniques, right? And the machine learning techniques means just finding which coefficients, right, is A, B, B2, Bm. I don't know that. I know all the x's, like this is the income for everybody. This is the debt to income for everybody. XM could be the FICO score for everyone. I know my outcome. I know whether I'm a 0 or 1. I know if I fail or not. But what I don't know, and what I would like to sort of leverage coding to find out, I don't know these coefficients. I don't know the weights. I need a computer to take the past data, crunch it, and spit these things out for me. Okay? That's the goal here. So what am I going to do? I'm going to use a library called sklearn. That's the machine learning library in Python. And I'm going to import logistic regression. And logistic regression just estimates for me this function. And everything sort of happens behind the scene, right? What's it? It was here, right? I'm going to create an object, a model that I want, and I'm going to fit my data, right? Fitting my data means I want to find coefficients. I want to find the relative importance of each of the factors I'm looking at, such that the data I have is closest as possible to the model, right? I want my model to fit the data as closely as possible. And then I can just print the coefficients, right? So this takes less than a second, right? Even on this Google Colab. And suddenly I have all my coefficients here. And the coefficients that we're interested in, right? This first one here is the intercept, is this free term here, A. We're not that interested in the A. But the other coefficients are the weights of each individual feature, right? So for example, the first one is 0.14. It's positive. This is a coefficient for home ownership. It means that if you own a home, your score will increase. If you own a home, you're going to be more likely to be successful at your loan, right? Because you have capital. The second one is income. If you have income, again, your score increases. This coefficient here is positive. So you're going to be more likely to be successful at your loan. The opposite is true for the third one, the debt to income. If you have higher debt to income, that's actually going to lower your score. Your coefficient is negative, right? If you are highly indebted, well, take a lot of loans, you're unlikely to pay them all back very, very easily. So that makes you less likely to be successful. And the fourth is the credit score, right? The higher your credit score, the higher your probability of success. All right, so intuitively, just looking at those four numbers, they seem to make sense, right? The signs seem to make sense. Like the model is not spitting out very odd predictions like higher income means you're less likely to succeed, right? But even then, what am I going to get? I'm going to get a number, a probability of success for each individual loan in my data, right? That can be 0, that can be 1, or that can be something in between. And the question is, most of them are going to be between. What do I do? What do I do if my model says somebody has a 30% probability of success? Do I give them the loan or not? And here you need to make up a more clear-cut decision, right? Because if you say, well, I'm not going to give them the loan because they're less than 50-50, well, they might still be successful and you're going to lose out on it. If you give them the loan below, even if you know that they're not 50-50, you might lose the money. And the problem is you don't know the distribution of the scores, right? This model will just give you numbers between 0 and 1, but it's up to you as the banker to figure out which threshold to choose. And I'm going to show you there are pitfalls in doing this, right? So let me open a new data set. We trained our model on some data on the first data set. And now I'm going to use a different data set of loans that the machine has never seen before to see how well it performs. And that's a key concept in machine learning. You always have 2 data sets. One, to make the computer learn about what's important in the data and what's not. And the second one, to test your prediction, to see how the model does. Is it accurate or not? Is it useful to distinguish between people who are going to pay back the loan or not, right? If you use the same data set, if you don't split it like that, and use the same data set to estimate the coefficients and to test the predictions, you're obviously going to be very good at testing your predictions, right? Because that's the data that you use to train it. Obviously, you're going to get something very close because you fit your model to that data. The real test is, how is this going to do in the future? How is the model going to handle with new data, not with the old data? Okay. So let's load up a test data set. And that's the second data set that we're actually going to use to test our model. Okay, we're going to do the same things. We're going to split it in the X's and the Y's. We're going to split out the 4 variables, right? The home ownership, the income, debt to income, the FICO score, and the loan status is going to be separate. And we're going to predict, right? We're going to predict whether those loans are going to be successful or not. Right, so here, if I look at the white pred, this is my set of prediction. I see a bunch of 1s, right? So the first loan is predicted to be successful, even though I can see here that it failed. The second loan is going to be predicted to be successful, although I see it failed, and so on and so forth. And that sort of brings out the problem in these models. They don't give you a decision threshold. And by default, the decision threshold is 50%. Everybody with a higher than 50% probability of paying back, they're going to be given the loan. Everybody with a lower probability, they're going to be refused the loan, right? In this data set, you can see everybody's predicted to be successful. Although that's clearly not the case, right? The first 5 people here have failed. So you perhaps want to be a bit more restrictive than that and choose a different threshold. So let's say I choose threshold 85%. I only give loans if I'm 85% sure that you're going to pay back. So let's set this Z. This is my threshold, 85. And then I'm going to make new predictions. Everywhere my predicted probability, given the data that I have, is larger than the threshold, every time I predict more than 85% probability that you're successful, I'm going to give you the loan, right? I'm going to give you a 1. If not, I'm going to give you a 0. So let's see how that looks like. Well, I can see that for the first person, I have a 0. I'm not going to give them the loan. And I would have been right in this particular case, right? Because they actually failed. So yay for me, that's a good decision. The second person with the high income, 197K, 710 FICO score, debt to income just 15%, and they own a home. Well, I guess this high income is going to make me give them a loan, right? So the prediction is 1. However, they failed. So in this case, my model made a mistake. It gave out a loan that eventually failed. So that's not bad. That's not good for me. The third loan, I would predict a 0. I would predict that it will fail. I will not give it out. I mean, look at here. The income is super low, 25K. Debt to income is super high, 28%. FICO score is actually the lowest I have seen so far. And I'm not going to give out a loan for that. And it's, I would have been right again, right? It's a 0 in the data. This person never paid back. So just by looking at the first 3 decisions, I have 2 right decisions, 1 wrong decision, right? But if I put the threshold at 0.5, I'm going to give loans to absolutely everybody. That's not what I wanted. Because then I would have been wrong twice in the first 3 cases. Okay? And then we have to sort of assess how many mistakes are we making. And that's a concept called a confusion matrix, right? And it's a 2x2 matrix. On the column side, I have the outcomes. Was the outcome positive? Did the borrower succeeded in paying back their loan? Or was the outcome negative? He didn't pay back the loan. And here I have my predictions. Is the prediction positive or the prediction negative? Did I predict that they're going to pay back? Or did I predict that they're going to default? Right? So where I'm right, I'm going to be right on this diagonal line. I'm going to be right in 2 cases. If I predict success and success actually happened, or if I predicted default and default actually happened. And I'm going to be wrong on this off diagonal terms. I'm going to be wrong if they were indeed successful, but I predicted they would default. Or if I predicted they were going to be successful and they indeed default, right? So in an ideal world, I will sort of minimize these 2 kinds of mistakes. In the data I have, I predicted success for 1,916, right? I was right in 1,695 cases, right? In most of the cases where I predicted success, I was actually right, okay? I was wrong in 221 cases. In these cases, I gave out a loan, but the outcome was negative. The person defaulted, so I lost the money. However, if you look at these mistakes, these are quite a few. A large part of the sample, I predicted a default. I didn't give out the loan, but the outcome was actually positive, right? The person actually paid them back. So I was very conservative with my decisions. I held out on a lot of loans that I might have wanted to give. In 837 of the cases, I was right. The people I predicted that they would default, they actually defaulted. Now the question is, what kind of error do I want to minimize? Do I want to minimize this error in which I give out the money and I lose them? Or do I want to minimize this error where I withhold loans from people that actually are good, that actually will pay them back. So let's try to push down the threshold a little bit. There's 85%. Let's say we want 75. So that means I'm more relaxed. I'm giving out more loans. I'm not just giving out loans to everybody with an 85% probability of succeeding or above. I'm giving out loans to everybody with a 75% probability or above, right? So everybody between 75 and 85 that were not getting a loan before from me, now they are. And let's see how that changes my, my mistakes. So I'm going to run this again. I'm going to rerun the prediction. How many loans do I give now? Well, I should give more, right? Because I'm more permissive. So instead of 1916, I'm going to give out 5,000 loans, right? I think that's probably everybody. Let's see the confusion matrix. So the confusion matrix, you can look at these four numbers. These four numbers correspond to the numbers in the matrix. I am actually going to be right in a lot of cases. I'm going to be right in 4,590 cases where I predict a good outcome, and the good outcome actually happens. So I'm going to give out many more successful loans. I'm not going to make as many mistakes as before, right? It's only in 268 cases that I'm going to withhold a loan from somebody that eventually ended up to be successful, down from 3,000, right? So I'm much less conservative. I don't withhold loans from people that are good, but I'm going to make many more mistakes, 4 times and more mistakes in giving out bad loans, right? Because I'm more permissive. So instead of giving 221 bad loans that didn't pay out, I'm going to give out 960 bad loans. All right, so it depends on what do I want to live with. Do I want to live with giving all these good loans, which is good for me, or having all these defaulted loans on my balance sheet? And it's a question of how to best balance these two. Now, if I go the other way, right? So this is, remember, it's for the 85% threshold probability. Let's say I'm even more conservative than what I showed you in the beginning, and I set a threshold to 90%. I'm only going to give loans to everybody with a score 90% or above. And I'm only going to give out 609 loans. Down from, remember, the baseline case was 1,900. So if I look again at my confusion matrix, I'm going to give out only 544 loans, down from 1,695, so much fewer loans. I'm going to withhold loans from successful people much more often, 4,000 loans compared to 3,000. But I'm going to be wrong. I'm going to give out bad loans only 65 times compared to 221. All right, so it's always a tension between how many good loans do I withhold and how many bad loans do I give. And what I want is sort of minimize both of them. And that depends on the model. If I already have a model, if I already estimated a model, whether this is the sort of S-shaped logistic regression that I show you today, or whether that will another sort of machine learning technique to make decisions, once I have a model that's sort of set, the trade-off between the two types of errors is there. I cannot sort of move it. I can only reduce the trade-off by implementing a different model, right? So the quality of a model is actually all in this picture. And I'm going to sort of explain to you. There's a lot of sort of code to sort of how to get to this picture. But what I want you to get away with is, how do I evaluate how good a model is? And remember, a model is good if it allows me to avoid both types of mistakes, both giving out bad loans and not giving out loans that turn to be good, right? So I'm gonna plot here two things, the false positive rate. So that's the percentage of bad loans that I have given out of the total bad loans that I could have given, how many of them I actually issued, and the true positive rate. How many of the successful loans have I correctly identified as successful? Okay. These are the two things I want to balance. A perfect model will be this green line here. That's the gold standard. That's what I want to achieve, right? I want a false positive rate of 0. I want to not give any bad loan. Out of all the bad people that are out there that are asking me for a loan, I want to give exactly 0 money to that. And I want a true positive rate of 1 or 100%. Out of everybody who's gonna be successful, I want to give everybody a loan because they're gonna pay me back, right? So the perfect model is able to precisely distinguish between people who are gonna give the money back and people who are not, right? So that's the green line here. That's the perfect score. It's never achievable in practice, right? It's an utopia of sorts, but that's where I'm aiming for. The blue line here is what am I gonna do if I just make decision at random, right? Well, if I'm gonna make decision at random, I'm gonna give, if I'm gonna say, well, 50-50, every loan, without even looking at the data, every loan I accept with probability 50%, right? Just toss a coin. Well, then I'm going to accept 50% of the bad loans, right? Because I don't care. I just want to accept 50% of the bad loans and 50% of the good loans, right? I'm accepting 50% of everything. If I set the probability to 60%, I say, oh, I'm just going to accept each loan with 60% probability. Then I'm going to accept 60% of the bad loans, 60% of the good loans, right? So the blue line here is just a straight diagonal, 45-degree line, right? I'm not using the data at all. I'm just tossing a coin or tossing like a biased coin and deciding whether to give the loan or not. Any sort of model that uses the data is likely to be somewhere in between these two extremes. Somewhere in between doing everything at random without looking at the probability that they're going to be successful or not, or being perfectly prescient and knowing in advance whether they're going to be good or not, right? So how to quantify the quality of the model? Well, if you're looking at this sort of geometrical shapes, is the area under the curve. That's what the machine learning people want you to think that, oh, this is the quality of the model. Like if you look here, this is like a square, right? It doesn't look like a square because of the way the figure is formatted, but it is a square. This is side, this is equal to 1. This is another side that's equal to 1. Right? So if you look at this area here, it's a square with the side equal to 1. The area is 1. That makes sense, right? The perfect model has an area of 1. Here, this line here sort of splits that square in 2. The area under the line is a half. So every model's quality is somewhere between a half for completely random and 1 for the absolutely perfect data model. This particular model that I showed you is the orange line, has an area under the curve of 0.6. So you're doing better. You're using some real data. You're doing better than the completely random, but you're still quite ways off the perfect model. A good model in practice would, if you get 0.7, 0.75, then you're golden. Then you're like, okay, this is a model that helps me distinguish, that helps me minimize the trade-off between how many bad loans am I getting and how many successful loans am I missing on, right? Because remember, I was playing here, I was playing with the thresholds. I was setting this to 0.9, 0.85, 0.75. I was trying to be more or less conservative, but that's only because I need to balance the two errors. And primarily, this is because my model is not super good and I am making errors, right? If my model was better, I wouldn't need to sort of change between being very conservative or very relaxed and just accepting a very large number of errors, simply because the model is better, right? The model allows me to distinguish between good and bad borrowers in a better way. Now, this particular model that I showed you, why is it not so good? Because it's simple. It's simple in two ways. I only use 4 variables, right? Home ownership, debt to income, income, and the FICO score. In practice, real banks would use tens or hundreds of variables. And it's not going to run in 1 second like my example code. So more variables allows you to fit the data better, allows you to get better models. Second, what you would need to have is better data itself, okay? More data, not just 5,000, 6,000 loans. That's very little. You need tens of thousands, hundreds of thousands of loans to sort of have more data to fit. And then your model is going to perform better. But even so, even for a toy example like this one, where we only have 4 variables and a few thousand observations, I'm still better to make predictions. I still can make better predictions than completely random. I still learn something from the data, right? And there are many algorithms like this, right? I showed you one, which is called a logistic regression, which just means I'll use this kind of a S-shaped function to get numbers between 0 and 1. There are other stuff out there. There are decision trees where you just go on a tree, yes, no. Does this person have a home? Yes. Does this person have a good income? Yes or no. And that will, each of these potential paths through the tree will give you a probability of success or not. And you will think, oh, this is just for loans. It's not. It's a very general technique that can be applied in many finance and non-finance settings, right? It could be applied, and it is applied in real life, in real time, to see whether a credit card transaction is fraudulent or not. Right? Remember, I don't know if you ever did that you pay somewhere and you get a text on your phone saying, oh, this credit card transaction doesn't seem like it's you, so we sort of blocked it, and then you have to either confirm it or call somebody. And it's the same kind of logic that goes behind that. You have a lot of data about your customer, and you're trying to map that data into a yes/no decision. Do I believe this is a fraudulent transaction or not? Right? And I don't know, variables there could include, well, has this person purchased from here before? Yes, no. How far is the business location from their home, right? Are they trying to purchase bread from a different city? That doesn't make sense. Are they traveling? Do they have an airline sort of charge in the past month? So you're trying to use all the past transaction, the address, everything you know about this person to make a decision. Is this likely to be them or perhaps not? And maybe I should withhold this transaction. And you have to balance these two kind of errors. You need a good model. If you're too conservative and you're going to label everything as a fraudulent transaction, then your customer is going to be very, very annoyed, right? Because everything they're trying to purchase, they're going to get a notification email saying, well, this is blocked, and they have to call you all the time. If you're very relaxed about it, then the whole service is useless because it's not catching any of the fraudulent transaction, right? So this is sort of the kind of trade-off you face, and the fact that you always want to improve your model. This kind of models are also used to determine whether an email belongs in junk or not, right? Uses variables like, have you ever received email like this from this person before? That they have certain particular keywords or certain attachment types that are likely to be spam or carry viruses. Every time you have a problem of prediction and a problem of separating between two categories, you can use this class of algorithms. Now, going sort of at a broader level is what kind of variables are you allowed to use or not, right? And what kind of variables is ethical to be using here or not? Is race, for example, a variable that you might want to use in that? And I think the consensus here is not. You cannot withhold a loan just because of a person's race or gender, right? And this is how biases in our society sort of feed back in the credit loan decision, right? Because if historically you're not giving loans to underrepresented population categories, or if systemically these people are disadvantaged, so they're less likely to pay their loans, then the computer is just going to spew a negative decision, and they're going to reinforce these kind of biases, right? So we have to be careful as to what we take into account when we design our models, what kind of variables we include, so we don't end up perpetuating this kind of resilient issues, right? For the credit card transactions, every time I try to buy food, for example, from TNT or from any other Asian store, I'm getting this notification that this might be fraudulent. Pretty sure they're using race. My wife is Chinese. She's doing the purchase. She doesn't get this. She doesn't get this notification. So it's not, I've talked a lot about the algo and the math going behind it, but part of designing these algorithms is sort of figuring out what kind of variables can we include and what kind of variables should we include, right? If we want to sort of not just parrot out decisions that reinforce inequalities. So that's sort of what I had in mind, and I see some attendees in the room, and any questions, comments, any sort of discussion for the sort of the last 5 minutes we have. You all have access to this. You can download it. You can play with it. It's all sort of like open source from my point of view, if you're interested. I'm gonna share again the link for the people who join later. And if there are no further questions or comments, well, thank you all for attending. I really enjoyed your presence, and please feel free to email me if you think about something later on. Thanks so much. Is there a Q&A? Yes, I see a Q&A. What advice would you suggest for people who are interested in getting more involved in the space? I would suggest, first of all, learning a programming language, learning how to work with databases. I think that's key. I teach a computational finance course here at U of T. People always come back to me and say, hey, this is really useful. Even at very traditional institutions, if we are going through the interview process, they ask us, hey, what do you know? How do you know to program? How do you know to code? Knowing Excel at this stage and is no longer, that does no longer cut it very, very well. Learn Python or C or Ruby. Any of these modern languages will do it. And then keep an eye for opportunities, right? There are obviously good opportunities in more traditional institutional hedge funds. There are a lot of these opportunities opening up in the fintech space, like in, for example, decentralized exchanges or new coin projects. A lot of these are probably scams, but some of these are really good and they will end up revolutionizing the way we think about finance in the next 15, 20 years. So taking the time to understand what's going on in that space and how sort of traditional finance blends in with this kind of Silicon Valley people, like the people behind, for example, Ethereum, I think is very valuable. And now a lot of the action takes place on Discord servers and things. So it's much more open than it used to be, and it's much more open to young people. So I think that there's a huge opportunity there. Which programming language do you think is best to use for this field? Many useful languages. So I think the best overall language, I would still say it's Python for now. I think Python is a bit of a gold standard in many applications. R is also very valuable if what you're doing is mostly statistical work. So not, for example, web scraping. I don't think R is very good at web scraping. Python is. Not if you want to work somewhere where latency is important, like the speed of your code, like the efficiency of your code. For example, if you want to go for high frequency training applications, you might want to look into C++, right? So it really depends on your application. I think Python is the most versatile and probably the easiest to learn as a starting point. And then depending on what you want to do, more HFT style, more data science, you can branch out. What part do you think decentralized finance will play in the future? Long-term technology or a new trend? I think decentralized finance is here to stay. If we can sort of get past these issues we have with a lot of cryptocurrencies that are scam projects, I think there's a lot of intermediation that has to be disrupted. I do research on stuff like decentralized exchanges. Right now, a lot of the, let's say, the profits, a lot of the gains from trading for everybody flows into the exchange. The exchange charges huge fees to have your computer there, to have access to their data. It's very, very expensive to have good quality data because exchanges will take their cut out of that if you want to be cutting edge. What decentralized finance will do, it will try to bring these platforms about in a more democratic manner. So I think the technology is here to stay. I think 99% of these projects, or the projects we have right now, will probably die out. Personally, I think Ethereum won't die out, but I don't take this as investment advice or anything of that sort. I think we would probably need a currency or a medium of exchange that's specific and that is versatile. That's something, for example, Bitcoin is not, because Bitcoin does not allow you to write smart contracts. Bitcoin is just a means of exchange. In Ether and the Ethereum blockchain allows you to actually build more complicated transactions, build more complicated contracts on top of it. So you would probably need something like that. And if you are able to make it faster, if you're able, whether trying to move from the proof of work from all this cost-intensive mining to proof of stake, which is much faster, if you can make it more efficient, then that's just going to increase its value. So I wouldn't necessarily invest in any sort of cryptocurrency or NFTs or things that are super volatile or super trendy, but I would keep an eye on the underlying technology. I think these advantages are going to be very important in the next 5-10 years into how to think about financial markets in general. I think we are moving to a world of decentralized exchanges, but they would probably look very different and less Wild Westy than what we see now. All right. Thank you.
Perfect. Maybe we'll, oh, I think there's one final question there.
Sure. I'll put my email here. Happy to chat with you guys. Yeah.
Perfect. So are there any final last questions for Professor Zoican before we close off? All right, seems like most of the pressing questions have been answered. Okay, so once again, thank you so much, Professor Zoican, for joining us, taking the time out of your schedule to teach us about fintech, loans, all these models, and also just share your overall valuable experiences with us. If I'm not wrong, I think Professor Zoican also has a quick research experiment or activity that he would like to share with everyone. So if you do have the time, feel free to check it out. I think it's based on the stock market, so it should be pretty entertaining. And for those on the recording or on the live stream, you can also check it out on our Discord. There should be a section titled FinTech Research Demo, where you can check it out there as well. So with that out of the way, I think that is all the time we have here for today. So that concludes our workshop session. Thank you all for coming out, and we hope you enjoyed Finovate. Thank you.
Thanks so much. And I'll post the link to the research in the Discord server.
Sounds good. Perfect.